Right. Hello viewers, we are looking at center of gravity, and under center of gravity we are going to consider this question. And so the question is, using analytical method, determine the center of gravity of the plane uniform lamina shown above. I did not include the dimensions, but I've indicated here that all dimensions are in centimeter. We are using centimeter for all these dimensions. So we have to label it accordingly. These are three shapes. This is a triangle, this is a rectangle, and this is a semicircle. So this is the first shape we are going to consider. This will be the second shape we are going to consider, and this will be the last shape we are going to consider. And so because it is a plane shape, it is not a shape like a cylinder. It's a solid shape, a regular shape. So because this is a plane shape, we are going to consider area. So in considering for the first one being the triangle, we are going to consider the triangle, and because we've labeled it with 1, we are using A1. So the area of a triangle is 1/2 base times height. Okay, this is the base. The base is, if you take 2.5 plus 2.5, that will give you the base here. To give you the base here, so that is 5 times the height. This is the height of the triangle, and so divided by 2. So when we do that mathematics, this is the base. From here to here is the base, which is the same thing as from here to here. So we have this. And then the centroid in the x-axis. Note, if you look at this shape, we have the origin, or what I call a reference point, for this other axis, for the x-axis, is from that is from this the end of the semicircle. And for our y, we are taking it from the bottom. We are taking, that is a reference point, will be from the bottom for y, and we denote it by L. And so in doing that, we have our x1. And because we are considering x1 for the triangle, we have to understand the fact that before we get to this point, we have this length from here to here. We also have another length, x, which is from here to here, before the length of the triangle. So what we do is, to determine the x, the center of gravity for this triangle, we have to consider this length, which is from here to here, which is the 2.5, plus this other one from here to here, which is this 5, before we now consider from here to here, because all these ones are in the x-axis, and because this is a reference point, we have to include it in our determination of the value of x for the triangle. So that's why we have 2.5, which is from here to here, and then we have 5, which is from here to this point, and then we have 5 divided by 2. Of course, we've come to the actual shape in which we are considering at the moment, so we know that it is always h/2. So that's why we're having 5, which is from here to this point, which is the same thing as this value, divided by 2. And so when we calculate that, we have 10 cm. And so we are done with that. We look at the y in the y-axis. That is this other axis. We are done with this axis. We are now considering this axis. So for the y-axis, I said our reference point is from the bottom. Like in the x, our reference point is from this point down. So, but for y, this is our reference point. And so, since we are considering this triangle for the y, which is this other direction, our reference point is this. So we have to also consider this value first before this. And so our y1 will be 5, which is from here to here, plus this from here to here. And of course, we know for a triangle, when you are considering the y, it will be h/3. And so that's why we're having this to be 5 divided by 3. So because this is a reference point for the y, and we are considering this other shape, we take from here to here first, which is this 5, plus the main shape we are considering now is 5, and the formula is that we divide it by 3. So that's why we have 5 divided by 3. So 5 plus 5 divided by 3 will give us that answer, which is 6.67. And so that is for the triangle. The next shape we are going to consider will be the semicircle. And the semicircle, the area of a semicircle is pi r squared all over 2. You know the radius of the circle is given to, the radius of the circle is 2.5. Okay, this is 2.5. So it means from here to here, that's the radius of the circle, is 2.5. And so when you pi r squared divided by 2, so the radius is 2.5. And when we bring in the values, we have this. And then for the x, as from this point, we are considering for this point down. So for the x of this semicircle, because it's attached to other shapes, this is the formula for calculating it. We have r minus 4r over 3 pi, because we are considering is attached to other shapes. So this is the formula for calculating it, r minus 4r over 3 pi. And so when we bring in that values, you are going to have 1.44 cm. And then for the y, of course, this is the y. This is what we are considering at this point. This value, this is what we are considering, and we are taking it as at a reference point. And because it is from here to here, and we know that from here to this point is 5 cm, so we just divide it, because the y for that semicircle will be h over 2, or whichever way. So you just have it to be this from here to here now is 5, so you divide it by 2, and then you have 2.5 cm. And then we are done with that. We go to rectangle. We know that the area of a rectangle is length times breadth. We have the length, and then we have the breadth. And so it will be 10 times 5, we have this. And then for our x3, for the rectangle, we know that if we are considering this axis, this is the x-axis, that's the LL, the reference point is from here. So for us to determine the x in this rectangle, first we have to determine this value first, because it is in the x. So that's why we have 2.5, which is this 2.5 plus. Also consider this, and of course you know the rule is you divide by 2, and so that's why we have 10 divided by 2, because from here to here is 10. That's why we have 10, and it's going to be divided by 2. But we have to also take into consideration this, because this is a reference point for the x-axis, and so that's why we have 2.5 plus 10 divided by 2. And when you work this out, you have 7.5. And then for our y3, for the rectangle, this is the rectangle, so it's just from here to here. And because this is a reference point, we are not considering this now, it's just this rectangle that we are considering, the height. So our reference point starts here, and so from here to here will give us that 5. And so when we have that 5, you divide it by 2, and then it will give you 2.5. We are done with that. And so for us to now determine the distance of centroid from the MM axis, this is the MM axis. MM axis. We have to use x, because the MM, the reference point, is this way. And if we are talking about LL, we are looking at from the bottom up. But if we are looking at MM, the reference point is this way, down to this direction. So I can say for MM, the reference point is this way, down to this direction. And for LL, the reference point is this direction, up. So we can say that MM is taking the XX axis, and LL is taking the YY axis. So in order to determine the distance of centroid from the MM axis, we consider the X, because the MM is moving towards this way. That's the reference point. So we have A1, the formula is A1 times X1 plus A2 times X2 plus A3 times X3 divided by A1 plus A2 plus A3. So our A1 is 12. Where is our A1? 12.5 times our X1, 10. We have our A2, this is our A2, 9.81 times our X2, 1.44. And then our X3 is 50 times our X3. A3 is 50, X3 7.5 divided by our A1 is 12.5, A2 is 9.81. And so when we do this mathematics and sum this, we are going to have 7.14 cm. What does this imply? It implies that the center of gravity from, or the distance of centroid from this axis will lie between here. Okay, let's look at it. We know that from here to here is 2.5, and from here, from this point to this point will be 7.5, because 2.5 plus 5 will be 7.5, and we have a centroid to be 7.14 cm. It means by measurement, if we measure a center of gravity, because from here to here now is 7.5, it means a centroid from this axis will be around, let's say, around here. That's what the answer implies. It will be around here. Or what I'm saying in essence is, from here to this point will be the 7.14 cm, because we know that from here to here, this is 2.5 plus 5, that will make it 7.5. So the interpretation of what we have as an answer here means from this axis, a centroid will lie around this direction, which is 7.14. So let's look at the distance of centroid from the LL axis. This is the LL axis, and I said in the LL axis we are considering it. The reference point is here, so we are going up in the Y direction. And so we still do the same thing, that our Y, the centroid in Y will be equal to A1 plus times Y1 plus A2 times Y2 plus A3 times Y3 plus divided by, rather, A1 plus A2 plus A3. And so when we bring in our values of A and Y1, A2 and Y2, A3 and Y3, we divide it, we have, the answer will be 3.24. Now let me interpret the answer here. What it is, what this implies is, from this LL axis, from this reference point of LL, it means since our center of our centroid from the LL axis is 3.24, this is what it implies. We know that from here to here is 5. It means our centroid should be, if this from here to here is 5, maybe 3 should be around this point. Let's say 3 should be around here. So which means our centroid, that is our Y bar, from this axis will be around here. This is where the centroid for this will lie. This is where it will lie. And then for the X, we are assuming that because it is 7.14 and we know from here to here 7.15, so we can assume that the centroid will act, that is X bar, will be from here to about this point. So basically, that is how to determine the centroid for this plane uniform lamina. I've done quite a lot of questions on center of gravity for solid shapes and for plane shapes, so you can watch out for my video to see those solutions. And if you're watching me for the first time, please do subscribe to my YouTube channel at Learn with Ephraim Afia for more videos, for also for you to get notifications whenever I drop a new video. Thank you.